In this example, we consider a mass spring system, so our classic damped and spring-bearing mass. And in this mass spring system, we're given a few pieces of information. The mass is 1 kilogram, the damping coefficient is 4 Newton meters per second, and the spring coefficient is 13 newtons per meter. What's interesting in this example is not the spring system itself, that's our standard one. The change is that we have an application of time-varying forces that turn off and on over time. So initially, if we look at y, our position, we're going to start this system out of equilibrium, and then at some later moment at time t equals pi, or approximately 3.14 seconds, let's write it as pi, we're going to turn on an external force. Up until that moment, everything is happening normally. So as a rough prediction, we would expect this mass to oscillate back and forth a few times. We don't know the period or anything yet, but it's going to exhibit this kind of behavior. And then we turn the external force on. And after that, well, I don't know what's going to happen. We'll have to see what the solution looks like. But it's going to be a combination of the natural oscillations and the oscillations driven by the external force. What's useful about the Laplace transform is that it can handle this transition, and in fact it can make the transition as smooth as the physics requires without us having to do any real additional bookkeeping. So we'll see how that plays out when we model this. From experience, we can write down the left-hand side of our differential equation. We've got mass times acceleration, and mass is just 1. We've got damping times the derivative, and we have 13, the k, times the position, and that equals F external. But let's not call it that right now. Let's go straight to a piecewise function. When we have 0 less than t less than pi, there is no external force at all. It's simply the natural internal forces of the spring system that are governing it. Afterwards, we're going to have a function that is defined by what's been given, 40/3 of a Newton. We'll see why the 3's there, it cancels nicely. But the key thing is that it's a sinusoidal external force. So we should see some periodic motion when that's done. But that only applies when t is larger than or equal to pi. Again, the strictly less thans don't really matter because Laplace transforms are integral based, and integrals don't care if we include individual points or not. All right, so if this is our differential equation, we're going to do a Laplace transform of it, which means that we really need to be able to write this in terms of step functions. And fortunately, when the only thing we have is this function turning on at t equals pi, then we can use our u notation, u sub pi, or the alternative u of t minus pi. Those are two equivalent symbols. I like the shorter one in practice. But that's all we need for our external force, because implicitly that function will be 0 when t is less than pi. So with this left-hand side and this right-hand side, we're ready to take the Laplace transform. To take the Laplace transform of the differential equation then, we need to remind ourselves that y of 0 is 1 and y prime of 0 is 0. That's our initial displacement and velocity. First, we'll move from left to right. We'll need the Laplace transform of y double prime. And going from our table, the transform of derivatives gives us the initial conditions here in order and decreasing s's. Then we'll have plus 4 times the Laplace transform of the first derivative. And that will be a little simpler. It's just sy of s minus the initial condition. And we'll have plus 13 y of s as the transform of y by itself. Now, the right-hand side here is a little more complicated, but if we focus first on the step function leads immediately to an exponential, e to the minus pi s, with a follow-up of a transform of exactly the same function, except with the t's replaced by t minus pi's. And here we use our knowledge of the sine function. The sine function 2 pi gets us to here. If we shift by 3 pi, then the function that we get after that is effectively equal to negative sine of 3t. It's the same graph, but it starts going downwards instead of starting going upwards. You can also use other trig identities to get to that. Simplifying the left-hand side is going to give us s squared plus 4s plus 13. All of those have y of s multipliers, and again we see our characteristic equation, the same coefficients as we have for the original equation. Minus an s, minus 4, s and 4, and there's a 0, and that's the entire left-hand side dealt with. And on the right-hand side, we can continue with our 40 over 3, the transform of sine of 3t, well, the negative sine of 3t, is going to be 3 over s squared plus 3 squared. And we can immediately tidy that up a little bit by canceling those 3's, which will make life easier for the partial fractions later on. We keep going with our goal of solving for y of s. First off, let's keep the multiplier on the left and simply move the s and the 4 over. So we'll have s plus 4 minus e to the minus pi s times 41 over s squared plus 9. And then y of s is going to have two components to it. S plus 4 over the s squared plus 4s plus 13 minus e to the minus pi s 40 over, there was an s squared plus 9, and now we're also dividing by this other quadratic term, and that is what we get for the transform version of our solution. We see a regular transform here that'll probably need completing the square, and we also have one here that requires partial fractions, and we have the indicator that there's a step function involved. So all these pieces are visible to us now if you have the Experience Center looking at the table and cross-checking it with the kinds of functions that we're working with. So our goal now is to find the inverse transform. To do that, we're going to need to use partial fractions to decompose this portion here. We can rewrite y of s as s plus 4 over, and why don't we complete the square while we're here? To get a complete square for this, we'll need to add a 4 and subtract 4 and add our 13 on the end. And that is going to equal s plus 2 all squared. The minus 4 plus 13 is plus 9. On the other side, we're going to have the 40 and the partial fractions. We're not going to go through all the gory details of this. It's a straightforward but just a lengthy calculation. What it will give us in the end, though, is the following. We'll have negative s minus 1 over s squared plus 9, and we'll also have s plus 3 over this quadratic, but that quadratic we also just said was, when we complete the square, s plus 2 squared plus 9. So our partial fraction decomposition gives us two linear terms over two quadratic terms, which is perfect for our inverse transform. And the last step before we're done is to regroup the terms. If we have an s plus 4 on top and we think of the transform of cosine, we need to have an s plus 2 on top to make that work. So if we have an s plus 2, this will be the transform of cosine with every s replaced by s plus 2. However, we had a plus 4, so we've only used up 2 of the 4, now we need the other 2 there. So this collectively is the original s plus 4. We're then going to do the same thing for these terms. The first one's fine. The second term, however, needs the same kind of cajoling. We have an s plus 2 here and we have an s plus 3. So we're going to group it as s plus 2 first. And that'll leave us with one more. So we'll have s plus 2 all over 9. So that these two terms add up to s plus 3. Again, what we're looking for is that matched set of s plus 2 and s plus 2 in both the numerator and denominator. Fantastic. Now we're ready for the inverse transform. And that gives us, we can go term by term. This will be an e to the negative 2t cos 2t. cos 3t, sorry. Here's our k, 3 squared. And the s's, that shift, is what gives us the exponentials. For the sine function, we have to be a little bit careful here. Again, this should be a 3 squared. For sine, we need a 3 on top, though. If we're going to do that, we have to also divide by 3. So we end up with 2/3 e to the minus 2t sine of 3t. And then we get the impact of the step function. Here we have this negative exponential, so that indicates that there is a step function. So we get that first. There's a negative outside, we just keep that. So all of the following functions are going to get turned on at time pi. Then working inwards, we have a negative s over s squared plus 9. That's a pure cosine. However, we always have to do this shift. It's the second effect of having this exponential s. We get a step function and we get a shifting. And the same thing is going to happen with the sine function. It'll be 3t minus pi's. And notice again, we'll have a little thing with 3's here. I need a 3 on top to make the sine function transform work. So we'll end up with 1/3 when we're done. And then we can move on to those last two terms, which are e to the negative 2t. These are similar to what we had before, except it's t minus pi times cos of 3t, but now it's t minus pi. And last but not least, we have the same 1/3 issue again. 1/3 e to the negative 2t minus pi sine of 3t minus pi's. All of those t minus pi's arising because of this exponential function, giving us a step and a shift as a pairing. So that looks a little hairy. Let's see what it looks like in piecewise format. It might make a little more sense then. In piecewise form, here's what y of t looks like. It is a combination of the two exponentials up until time equals pi, so from the start of the simulation until time equals pi. And the reason for that being the only two functions in play is because the other functions, all the other 4 functions, are multiplied by u pi. And again, that u pi means on, at, and after t equals pi. So these don't even turn on, they're not even present until that later moment. These first two functions, though, are always on. There's no ever turning off of them. They're not subtracting by any step function. So there we get those same functions again, plus all the ones that had the u pi multiplied once we get past the interval time pi. Now this can be hopelessly complicated. We'll look at it graphically in a moment, but there are some insights that we can gain right away. On the interval 0 less than t less than pi, what we basically have is an e to the minus 2t cos 3t sine 3t. And we know what that graph looks like. It's going to be some decaying exponential. And we could talk about its period and its frequency, and we could talk about how fast the decay is occurring. When t is larger than pi, what do we have there? Well, we have the same combinations. They're still basically exponential times coses and sines. The shifts here don't change that form dramatically. So we still fundamentally have exponentials with cos of 3t's and sine of 3t's. And those are going to do the same kind of pattern. They're going to be exponential but decaying oscillations. And we also have, though, we have the cos 3t and sine of 3t. And those are oscillations that'll continue forever. And what we're doing is adding those two together. Well, if you think as time gets larger and larger and larger, this term is eventually going to disappear, and we're going to end up with this term here, which would be our steady state solution. So we have some interesting things happening at the start, at the onset, when t is less than pi, some exponential decays, plus some effects that are going to decay after that. And at the end of the day, though, we're going to be left with an oscillation that's driven by, notice where that comes from. It comes from the oscillations in the external force. The fact that we keep pushing and pushing and pushing and pushing on this system leads eventually to a steady state response to that oscillation.